Now let's turn our attention to example number 6. Here we want to suppose that we have a vector field given by this horrific formula, or set of formulas, and we suppose that sigma is the hemisphere that's given by this sphere. Notice it's a sphere with radius 4, but where y is positive. So notice here in my picture, I've kind of gone ahead and rotated my axes so y is pointing up as opposed to z. But again, everything here still follows my right-hand rule, which you could check. Now, this is going to be oriented in the direction of the positive y-axis. You can see here that all of my kind of arrows, my orientation for the surface, are pointing upward. They're tilting up towards the y-axis. I don't have any arrows that are going to be kind of imagined as pointing on the inside and coming out, because that would not be in the orientation that I'm interested in. Okay, so what we want to go ahead and do then is to try to find the exact value of this surface integral. Notice that I can kind of almost imagine this as like a flux integral, because my curl of f, again, is a vector, and you might keep in mind that my ds over there, we often thought about it a couple sections ago as expressing as n dotted with ds. So this is just a classic flux integral. It just happens that now the vector field I'm using is the curl of the vector field f, which itself is another vector field. So if I want to compute this, again, I could do this directly. There's nothing wrong with doing this directly at all. I could go ahead, find the curl of this, which looks to be horrific, but we could try. I can already easily see that, again, I could maybe define this here pretty easily as some sort of a function, or maybe I could parameterize it using spherical coordinates, and I could replace my n with all the pieces that I need, and I'm on my way. Of course, if I want to try to do this, I'll recognize that a lot of these pieces are going to be kind of messy. It's messy to work with spherical coordinates. It's messy to go ahead and try to do a bunch of partials of this, and I'm sure the curl here is going to just look horrific. So instead, what we will choose to do is to try to use Stokes Theorem. Stokes Theorem, remember, will say instead of computing this, we can try to go ahead and compute an f dot dr, that is a line integral, where c is the curve that is the boundary of our surface. So let's see what we have here. So I'll start by saying that we see that the boundary curve C for sigma is a circle in the xz plane. You can see it actually right down here. This right down here would be considered the boundary of that surface, because notice that that's like, if you cross that line, that's when you would switch to being like outside of this hemisphere to almost inside. That's the edge of it. And actually, I can easily see that if I was in the xz plane, then that means, of course, that y is 0. But if y is 0, then this equation simplifies, and we could say that the equation of that circle is going to be x squared plus z squared is equal to 16. So that's a circle down there with radius 4. Now, if this down here is my curve C, I'd like to give it positive orientation. I have to remember that because I have my arrows pointing upward here, when I draw my little person standing on this curve, they have to be standing with their head up as opposed to, their head being down like this. So that person I don't want. I want the one that's facing upright, same direction as my arrows. And I have to imagine what direction do they have to walk around this particular circle in order to keep their left hand touching the surface. Well, it seems like they would have to walk this direction. They'd have to walk from the positive z towards the positive x-axis. So they'd have to walk in this direction. So I'm going to go ahead and summarize this with the following picture. So I'll say we give C a positive orientation. Let's see how I can go ahead and sketch out what that would look like. So let me just sketch out a quick circle here. Okay, so let's assume that we have this. And we've gone ahead, we've given this positive orientation. Let's assume that this right here is my x-axis and this is my z-axis. Our positive orientation, notice, again went from positive z-axis and swinging down towards my x-axis that was positive. So this right here is the positive orientation. I'm moving in this direction around that particular curve. Now, once I have that positive orientation, if I want to, instead of computing this double integral over here, I want to compute this line integral, I'm going to need to understand a parameterization for C. So I'll say we parameterize C as, well, let's see what we got. This is again pulling on a lot of knowledge that we used at the start of Chapter 5. Well, I want to create a parameterization that creates this circle rotating in this particular direction. Now, we know how to create circles. We can try to do some things like a cosine of t, and notice I'll put 0 for y, since y is always 0 on that circle, and maybe sine of t. Now, there's no guarantee that this is going to work right now. We might have to tinker with this a bit more. Remember that we wanted this to be a circle with radius 4, and right now, I don't have circle radius 4. This would be a circle with radius 1. But you might recall that if I was to put a 4 as a coefficient up here, that would create a circle that actually has a radius of 4. Now again, while this creates a nice circle, I want to make sure that it has the appropriate orientation. And I can test some points to just quickly see. Let's see where we're at if we plug in t as a 0. If we plug in t as a 0, we're going to be at the point 4, 0, 0. So we're going to be like right here. What would happen if I plug in, say, something like a pi over 2? So as I increase the t, I want to make sure I go this way. Well, if I plug in pi over 2, I'm going to be at 0, 1. I'm going to have moved up here. So that's not what I want. This is the incorrect orientation of this particular curve. So I might need to make some adjustments. So let's see. I like the 4s, but maybe I can get this to swap around just a little bit. An easy way sometimes to change the orientation of a curve like this is to just interchange the locations of the sine and the cosine. Notice now, if I plug in 0, I'm going to start at 0 with a 1. So I am going to start up here. If I now plug in something like a pi over 2, I'm going to get 4, 0, 0. Well, that's going to be over here. I will have moved from this top point down to here. And that's moving in the direction that we want. We also just have to specify the bounds on t, but those are pretty easy. We're going to go from 0 to 2 pi. So now that I have this, it's ultimately very, very simple to use Stokes' theorem. So I'll state down here, by Stokes' theorem, my double integral over sigma for the curl of f dot ds is equivalent to my line integral over c of f dot dr. Now you might remember the way that we can typically set this up. I'm going to change everything in terms of t. So I know that my bounds on my integral are going to go from 0 to 2 pi. I want to rewrite f, so it's actually going to look like my vector field, but just with my values of x, y, and z plugged in. So let's take a look at what each of those is going to ultimately look like. We're going to have, let's see, z times e to the y. So if y is a 0, that's just going to be e to the 0. That's a 1. So this first component is just z. So this is going to be 4 cosine of t. You know, actually, I'm going to go ahead and rewrite all of this on a new line just so I make sure I have enough space. So let me go ahead and move this down here. So 0 to 2 pi, and I know I'm going to have a 4 cosine of t. Then I'm going to look at my vector field f and see what my middle term is going to look like. Let's see. It's going to be x times the cosine of 0. Cosine of 0 is 1, so it's just going to be a 4 sine of t. And my last component here is going to be x times z times the sine of y. Well, the sine of y is 0. So sine of 0 is 0. That whole last term then is just, or whole last component is just 0. remember that to replace my dr, I essentially can do an r prime dt. You might recall that that's a way that we often thought about kind of reworking this. I'll go ahead and jot this down up here again since it's been a while. But we often thought about saying that I would take my vector field and rewrite it in terms of my parameterization r, and then I would have my r prime of t dt sitting at the back. So notice if I take my r prime here, I'm just going to get 4 cosine of t, 0, and then negative 4 sine of t, and then dt. If I simplify this down, again, this here is a 0, I have an integral from 0 to 2 pi, and the dot product here is very simple. Notice that the last components are going to just turn to 0, the middle components are going to turn to 0, and I'm really just going to have a 16 cosine t squared dt. And I'll go ahead and finish out this integral here. I have to make sure that I understand how to use some trig identities in order to be able to finish this evaluation. I might recall that a cosine squared is much easier to evaluate if I use the trig identity 1/2 times 1 plus the cosine of double the actual angle. Now, of course, I'm going to get an 8 here, so let's go ahead and just pull that outside the integral. And so I really just have to go ahead and attempt to integrate this stuff here. That's going to look like 8 times t, and I think that should be like a sine of a 2t, but probably with a 1/2 to catch the 2 that's going to come out from the chain rule. If I evaluate that from 0 to 2 pi, I'm in business. So let's see what we come up with. I'm going to end up with 8 times 2 pi plus, let's see, the sine of 4 pi is just going to be 0. And then I'm going to have the sine of 0 is just going to be 0. So this whole piece is 0. And really I just end up with 16 pi. So again, we've been able to find this flux integral, that is something like how much fluid would pass through the surface, but we were able to do it by instead looking at the boundary curve and computing the work that it takes to kind of go around it. So this is the interesting connection that occurs with Stokes' theorem. Now, the remainder of the questions or examples in this section, as I state here, are a bit more conceptual in nature, and they were really only going to be covered if time was permitting. And since we're in an online format for this class, for this particular section, I'm going to go ahead and not choose to cover those in the video. I would ask you instead to spend your time trying to go through the worksheet problems associated with this section. And if you're interested, you can take a look at those extra problems at the end of this section in the notes on Blackboard. And of course, I'd be happy to answer any questions about those if and when you have them.